Welcome, everybody. Today we have a presentation about DAS for induced seismic monitoring application in mining infrastructure and earthquake detection by Zara Anderson from Sintela in Canada. Please, Zara, the floor is yours.
All right. Thank you very much, Safka, and hello, everyone. Good morning, good afternoon. And I appreciate the opportunity to be here to share some of our learning and experience with DAS in induced seismic field. I'm Zara Anderson. I'm based in Ontario in Canada, and I work with Sintela, which is a UK-based company, and DAS manufacturer and provider. My background is a mining geotech engineer. I'm not a seismologist, and I'm not an expert in fiber optics. But what I'm sharing today is what we've learned over the past 5 years or so, looking at how we can implement and deploy distributed fiber optic sensing technology specifically for mines within my area, but it also has applications outside mining for monitoring. So if you guys are familiar with that, you probably have dived into it. If not, this is kind of a high-level summary. So let's get started. Yeah, so distributed fiber optic sensing, or DFOS, it's a technology that basically uses the standard fiber optics cable, and I have some fiber optics cable here as an example. It's quite light and flexible, and within the fiber cable, we have multiple strands of fiber. These are just fiberglass core, and we can connect an interrogator, which is I always call the heart of the system, to this fiber optic cable and turn the fiber itself into an array of sensors. So the way the system works, the interrogator keeps sending rapid laser pulses into the fiber optics cable, and there is a backscatter light generated. I oversimplify it, but that backscatter light going to the interrogator, depending on its type and its characteristics and phase and frequency, it can provide information on multiple parameters all along that fiber optics cable. So the fiber can be deployed for 1 kilometer, or it can be hundreds of kilometers. We can do measurements of temperature, strain, and seismicity all along that cable. So some of the features of this technology, it basically uses that standard fiber optics cable. It's low cost and it's durable. If we install it and deploy it properly, it can provide data for many decades, as long as we have the interrogator at the right time. It's light-based technology, so there's very little electrical interference with other equipment. We can do multiple measurements of strain, temperature, and seismicity on that one cable. We do need different interrogators, but I dive into it a little deeper. The high spatial resolution, we can do measurements as small as every 25 centimeters, typically every meter or so, for data management. High location accuracy, so within a meter or so, we can locate a temperature event, strain event, or seismic event, depending again on the cable layout for seismicity. For DAS application, which is distributed acoustic sensing, we have a wide frequency range from millihertz to over 50 kilohertz. That really opens up the applications of DAS for seismicity and acoustic measurements. High acoustic dynamic range of over 120 dB. Real-time data processing, and there is a lot of advancements in this space. That has been, one of the challenges of DAS specifically, but that's rapidly overcoming. And it's really suitable for harsh environments because we are dealing with fiber optics cable that can be manufactured for really high temperature areas or high pressure applications such as oil and gas. And with enhances in data analytics and AI power, I think DAS really gives us a lot of that opportunity to do large scale a high resolution monitoring at much faster speed as we improve the data processing routines and algorithms. So the common type of interrogators we have, today I'm mostly focusing on DAS for distributed acoustic sensing, and that's where we use geophones or accelerometers. But there is also DSS for distributed strain sensing and absolute strain measurement, and DTS for distributed temperature sensing. So DTS and DSS are usually near field, so within approximately to the fiber location, we can measure strain changes if the fiber is nicely coupled to the rock mass or to the infrastructure we're monitoring, and also for temperature variations, if anywhere along the fiber there is any temperature variation, we can monitor that. But the benefit of DAS is that it's far field, so fiber is sensitive to any kind of dynamic seismic activity or dynamic loading coming towards fiber from a distance as well. So DAS is far field. So distributed fiber optic sensing evolution in late 1980s, it was the first DTS system based on the Raman backscatter light that we started to develop for temperature sensing. DTS, typically its performance is within kilometer scale range. Within a kilometer, a couple of kilometers of fiber, we can do temperature measurement with 1 meter resolution and temperature accuracy of ±1 Celsius. It's within millihertz bandwidth. In the 90s, we started to look at Beryllium backscatter wave, which is used for both distributed strain, absolute strain, and temperature sensing. The DSS performance is also in the tens of kilometers, longer than DTS. The resolution is centimeter to meter, and its resolution in terms of a strain is microstrain, and it's again within millihertz bandwidth. DAS, or distributed acoustic sensing, it was mid-2000s, so it's still fairly new. For that phase, a sensitive OTTR-enabled DAS application that started to advance, and it converts basically the standard telecom fiber optics into an array of geophones laid back to back every meter. So DAS's performance is for tens of kilometers for long distances of fiber. It's meter resolution. The strain resolution is quite high. It's picostrain sensitivity, and the bandwidth is tens of kilohertz. So as I mentioned, from millihertz to over 50 kilohertz bandwidth that we can measure with that. So just a quick animation of how DAS works as we send fiber optics, as we send laser pulses into the fiber optics cable. There's those impurities in glass that cause backscatter. That backscattered light goes back to the interrogator. And if there is a seismic event, that changes the phase of that backscatter light. And from there, we can do measurements of the strength of that seismic event and the location and frequency and phase of it. So as I mentioned, picostrain, it's far field, and it's suitable for dynamic monitoring like seismic activity or dynamic loading, especially for deep underground rock, hard rock mines. That opens up a lot of applications for monitoring the rock mass response as well. So in a lot of distributed fiber optic sensing applications, the way we plot the data is called a waterfall plot. It's basically depth or the length of the fiber over time. And every time basically optical signal is sent through the fiber, and every time there is a seismic event or a dynamic event, that interferes with that backscatter light, and then you can see that dynamic strain response on that waterfront plot and depth over time with the strain, picostrain sensitivity. So going into a couple of applications of how we use DAS, this is in the slow strain dynamic strain event. This is an application in oil and gas industry, but that slow strain of DAS, it's a measure of But basically a strain rate is a measure of how quickly a material deforms under strain. Under stress, it's defined as the rate at which strain changes with respect to time. So it's particularly important in dynamic loading conditions where the speed of deformation really affects the material behavior. It's like that, how plastic or how elastic a material is. So again, as I mentioned, for underground deep mining, for example. So in oil and gas, we use fracture hit as the parameter for that low frequency strain response to a fracture front propagating across fiber. So this is a model to demonstrate that. We have a monitoring well and we have an injection well for a hydrofracking application. When that injection happens, it creates fractures within the rock mass. And here you can see a fracture propagating. So at the tip of that fracture, we built up that tension area, that red zone showing tension. And then as the fracture propagates, you can see the blue zone. So that's the compression area around the fracture site. So this model, this is the data on depth in real time, depth over time. And you can see as the pumping starts, and fracture starts to propagate, we can see that strain response, that fracture front, that fracture hit. And then as the fracture propagates, we see the compression zone, but also throughout the pumping, we can see more fracture hits and more fracture fronts propagating. So in oil and gas, this is a very standard solution and process to look at the fracture propagation and understanding the production of that oil and gas well. And then when the injection stops, we can see that everything relaxes and the compression builds and we don't get any more fracture hits. So this is slow strain. It's only visible on DAS because of that low frequency, less than 1 hertz response. We have used it also for mining applications for monitoring. So this is an example of a mining application where we have fiber optics installed from surface for about 160 kilometers at the site of a block cave application. And you can see again the waterfall plot here, fiber distance over time, and the strain rate in and picostrain resolution. So as time goes by, every time there is that fracture propagation building up, you can see early signs of it on the strain response of fiber optics. And before that fracture propagates and breaks and the rock mass breaks and the fiber breaks with it, we see that increased response in slow strain. And then fiber gets cut, and then we continue to monitor on the remaining of the fiber for that slow strain response. So this is used for early kind of indication of damage, so for response and moving people or equipment from the production area or the hazard area. So that's on the slow strain side in mining. With that, we also can do seismic monitoring as well. So an acoustic wave propagating across a cable. Here you can see a seismic event schematic propagating seismic waves. And if we have fiber optics, those impurities cause the backscatter light. So if fiber optics cable, we define it into channels every meter or so. As the seismic event gets away from the fiber, we can see that basically arrival time as well changes with that distance to the fiber optics cable, kind of very, very similar to geophones. And we can measure phase frequency and amplitude equivalent to a geophone. But with fiber, we get that better low frequency response as well. So yeah, this is just an example again of a fiber optics cable over 4,400 feet. Over time, that waterfall plot, and you can see the P wave all across that 4,000 feet, S wave, as well as those other details of P and S wave conversions. So basically, every time a seismic event hits the fiber, it causes fiber cable to compress or stretch very slightly, very sensitive. And the energy of that seismic event dictates how much strain we get in that fiber. and that changes the backscattered phase. And from that, we can measure the amplitude, frequency, and arrival time of that seismic event. So in mining, we have used the technology for rock mass response monitoring and block cave mining. Not sure if how many people are familiar with it here, but it's an application for low-grade or massive rock masses, ore bodies, where it can be a couple of 100 kilometers underground. We build the infrastructure under the ore body, and then we let the material to fall under its own weight and propagate. So as you can see, because of its larger scale, it's very hard to monitor the rock mass response with traditional instruments or even with visual assessment. So in this case, we can put fiber optics cable from surface to deep boreholes, a couple of 100 meters. Or in this case, and the next example, we had 2 kilometers of fiber optics. It can be within the future ore body or around, and it's fairly easy to install fiber optics cable. Within a couple of hours, fiber can be installed, can be grouted, and then it can be monitored and used to monitor the range, the largest scale of that block cave. So we can do it for high resolution tracking of the yielded zone, which is that kind of area where the rock mass is fracturing and the fracture is propagating and there's tensile strain. We can see those areas with strain response of the rock mass, of the fiber, and combination of DAS and DSS. We can use it to look at the seismic clusters, which is in that area of seismicity where the stress is building up behind the yielded zone. So there's a cluster of seismic activity, and there is indication that we can even see early response of that elastic region, which is further away from the active fracturing zone, but the rock mass has started to respond to that cave propagating coming nearby. So those tiny tensions and compressions can be indicated as well with the strain response of the fiber. So here's an early kind of a schematic of what was done in one of the block cave applications. From surface to the boreholes were deployed, fiber optics installed, and then the fiber optics, we use bottom hole assembly at the bottom of the borehole just to turn the fiber around on itself, and then daisy chain it with another one to extend the coverage of the seismic network, basically. And because we dip the boreholes slightly to help with better location accuracy of the seismic events rather than 2 exactly parallel boreholes. So that kind of dip is enough to give us a better location accuracy of seismic events. So here's the cluster of seismic activity, and here by rock signal some of the processing data. So the block cave was propagating on the side, the 2 boreholes at around 1.5 kilometer deep each. We're monitoring with DAS, and what's interesting that we can see a range of magnitudes of seismic events from small magnitude to large magnitude. And you can see the smaller cluster of seismic events picking with this with DAS. The smaller events show that yielded zone, that the fracturing is propagating. It's yielded, it's not high stress, it doesn't generate high seismic events, and it shows where the next cave back is, which is quite interesting. But then on top of that, we see a cluster of larger magnitude events. And this is the area where the rock mass is building stress in response to that cave propagation and stress redistribution. And that large magnitude cluster, as you can see, it's not quite in parallel with the smaller cluster. So it shows that the block cave is actually propagating in relation to the geological stress and geological structure as well as the stress distribution. So it's not that nice even dome shape that we would want to have in the block cave. So it gives you a much better indication of how the cave is propagating and how the rock mass is responding. And this is another application, again, for DAS and for hydrofracking in a deep underground mine. So a lot of deep underground mines, as we go deeper, the stress is becoming a major issue. And sometimes ahead of mining in a certain area, Preconditioning is done, hydrofracking is done to basically create fractures within the rock mass and soften the rock mass. And that has been used in addition to geophones in some applications to look at the response of that preconditioning or hydrofracking. So in this example, again, there was 3 short boreholes daisy chained together. These were deep boreholes, a couple of 100 meters each, daisy chain. And with just that, for a couple of weeks of monitoring, we could see not only the response of seismic related to hydrofracking, but as well as the seismicity within the mine, both development, blast, and seismic activity. So the other application of DAS that can be very useful is for tomography. This is just a schematic showing that if we have a low velocity zone versus a high velocity zone of black, and if we have 2 boreholes with each borehole having 4 geophones in them, and some yellow dots showing as seismic sources. So if we were to do a tomography in this area, because we have limited ray pads, the resolution of those high velocity versus low velocity zones, it's really hard to define with a number of seismic events and a number of geophones. However, if we instrument these boreholes with fiber and do measurements every 5 meters along the fiber, so it's still at 5% DAS resolution, then we get a lot richer ray tracing, and with that we can get a much better understanding and definition of those low velocity versus high velocity areas. So this is an area for real-time tomography with DAS that can be done in underground mines, for example, and this is just a comparison. So low velocity geophone with lower number of ray tracing versus DAS. So if we have fiber in boreholes in certain areas, and we can use either the blast or the seismic data or active noises to create more relatively real-time tomographic images. This is, I think, something that has great potential. It's not, as far as I know, implemented anywhere in real time, but there is quite some good work being done by a number of companies in this area. So an application of seismic imaging, again, is within tailings dam monitoring or embankment dam monitoring. Distributed fiber optic sensing is becoming a more known technology to be useful for dams. So we can use the DTS and DSS in dams connecting to fiber optics for that near field temperature and strain measurements. With DTS, because we can sense temperature variations, from there we can measure seepage and look at internal erosion. With DSS, we can look at movement and settlement. With both of them, really the layout of the fiber is important, where the fiber is installed and how it's deployed. But there's also a lot of potential with DAS for monitoring dams and infrastructures and tailings dams. With DAS, because it's far field, we can do a range of seismic activity and monitoring, active and passive. However, it's also more challenging. I think it's just because, especially with tailings and embankment dams, it can cause a lot of ambiguity, but there is a lot of good work, again, going on in this area as well. Some of them is related to ambient noise tomography. So ambient noise has been used with geophones in tailings, and a couple of examples of ambient noise with DAS has been done as well, where because DAS is as far field, in this example, DAS was only deployed on the crest of the dam, and we were able to kind of look at the velocity variations within that structure at depth with high velocity and low velocity. So in a lot of tailings dams, what that can be done now, if the fiber is deployed, DAS doesn't have to run all the time. So we can do a survey, do a seismic image, ambient noise, and then repeat it in 6 months to a year and just see what variations we see and if there is any signs of internal erosion within that structure. And there are a lot of hydro dams that now are deploying fiber within the structure as they build the dam. so then they can use it for that ongoing seismic surveys in the future. It has also been used outside mining in infrastructure monitoring. This is a recent example that showing on the map on the left where DAS was deployed onshore between China and Hong Kong on a bridge as well as a tunnel. So I think altogether it was about 30 to 35 kilometers of fiber deployed, and there were measuring activities onshore as well as the vehicle and the traffic on the bridge as well as the tunnel. And there were some measurements of seismic activity within 200 kilometers. So these are seismic activities of magnitude 1 to 2 that were recorded on that fiber on the bridge. And also looking at the maintenance of the bridge as well, looking at the vibrations and looking at the distances between the bridge piers, and looking at also the velocity, the speed of the vehicles, and if there is any maintenance, so that can become a routine. So that was an interesting paper as well. I have the link below as well if you're interested to read more about it. And DAS in earthquake monitoring, I think everybody probably has heard that it's becoming more and more common to use the existing communication fiber optics cable for earthquake monitoring. There is a lot of fiber optics cable within the cities or ocean floors, and that's becoming more common for that. So this is an example of an earthquake. At the bottom, you can see the PNS wave arrival recorded on the cable off the coast of California. This was an event of 18 kilometers away onshore of a magnitude 2.8 event that was recorded with that cable. This is another example that we did some monitoring in Alaska, 2 fiber optics on the seafloor as well. You can see a dense seismic event, clusters of events being recorded. And it just shows, the fidelity of that cable and the ability to detect relatively weak events at depth. And this one is at a depth of 156 kilometers with a magnitude of 1.8 and the PNS wave arrivals. If you're also interested on the Sintela website, there is a live demo of or a live recording of this DAS at Sakurajima Island in Japan. It's a volcanic island, residential, so fiber is deployed all around the island and some inland fiber optic in red. And so there's also live cameras showing the volcano. So you can see the waterfall in real time, and there's been a number of seismic events recorded with that cable. So if you're interested, the links are here as well. So in terms of DAS and geophone integration and data interpretation, so prior to that, I was using geophone-based systems for seismic events, and they are developed. They're very advanced, and it's still #1 monitoring system for seismicity in mines and a lot of induced seismicity applications. A lot of people are interested to deploy DAS, but I want to know, can they integrate the data or not? So I thought I'd just put a couple of slides there. So again, in an underground mine example, typical, we use boreholes. We put fiber optics in boreholes and daisy chain them using bottom hole assemblies to extend that seismic array coverage. But in civil applications, there are other different ways to have extended lengths of cable to extend that network. Once that cable, that fiber is deployed, we typically want to use one DAS unit for cost efficiencies and optimization, but we can use multiple DAS units as well, and then do measurements. So being quiet. Yeah, so with geophones, as everybody is familiar, geophones, we measure the voltage proportional to that velocity of the mass in the spring. With DAS, it's backscatter light in that pure fiber glass. So that backscatter light is the strain rate. It's we look at the gauge length of that fiber, of that measurement, and we can look at as the fiber optics, as the waveform hits the fiber optics, it changes that picostrain change in fiber, and then we'll look at over the gauge length, we do an average of that strain at that accumulated strain over that average. So that strain rate, that strain change in time, we can record with fiber, and from there we can get the frequency, phase, and amplitude of that seismic event. So we can change the strain to velocity. The other way around is not as easy, but looking at kind of the background here, again, seismic event coming in green, and fiber data. This is from geothermal application in Utah, but geophones overlaid fiber. You can see the P and S waves are very much in line with what we get from DAS and geophones. With DAS, we of course see a little more details. So we can change the strain rate to velocity and do measurements and integrate the data. Velocity to strain is a little more tricky, but in terms of comparisons of DAS versus geophones. So DAS is not yet as advanced as where geophones are in terms of all the calculations and measurements and real-time systems. With geophone systems, the seismic event happens in real time. You can see where that event is, what the source parameters are, and the details of the location accuracy. With DAS, it's still early stages. There are differences. So with DAS, the one advantage on the left here, you can see the possibly better location accuracy. So this was from CSIRO publication, where we have DAS in vertical, and I think this was a coal mining application, DAS in vertical, and then on surface in X and Y directions. So with an event location, with just the apex of that event arriving on these three, but just looking at that, we can locate the event. So that reduces the ambiguity of the velocity variations, wave velocity variations, especially in underground mines with constant mining. So that's an advantage. If they have the right fiber cable in the right layout, we can get a better location accuracy without relying on the velocity model. Source parameter, again, because source parameters have been established based on geophones and velocity and acceleration. With DAS, we measure strain rate. We can convert that. So there has been a lot of good work the last few years to show that there is really good consistency between DAS source parameters and geophone source parameters. And currently, if we have a couple of geophones and we have a DAS system, we can calibrate and get the magnitude and source parameters from DAS for geophones. But I think as the technology enhances, we can get more real-time, better source parameter calculations with DAS. And then moment tensors, there is possibility of being able to do better moment tensor analysis with DAS, again, because of that rich, high aperture waveform coming on a larger length of fiber, and we can see the phase changes more clearly. As everybody knows, DAS is more of a uniaxial component. So again, the layout of the fiber and how we can overcome that. We don't have that triaxial component that we have in geophones and accelerometers. So that's one of the issues with DAS to keep in mind. A lot of DAS units are one channel, so it has to be the way of laying cable is important to get the maximum of that one DAS channel. There are DAS channels that are DAS units that are two channel, but it's there are different ways of deploying the cable, the fiber optics to maximize coverage, but also redundancies. If we have fiber breakage, there are multiple ways to avoid losing a lot of the seismic array. So we don't go into the details of that discussion, but these are some of the things to keep in mind if we are looking at the DAS deployment. Moving on, I think I've got a few minutes left. So yeah, I think really for DAS applications, what we've done, especially in underground, because we have that kind of software-defined frequency range, we have used it for blast detection. This is a blast example where 3 millisecond raw data, we can see the seismic events, the blast events coming in and missed shots identified. We can use it for microseismicity, BSP, surface seismic. And a lot of advanced software that we have today, we can build that kind of processing tree and engineering processing routine to look at the raw data and extract multiple ways of detecting blast and detecting seismicity and detecting events and walking and everything with that engineering tree that's quite kind of user defined. So moving on, advances in DAS technology, I thought I should mention this as well. This is still a fairly new technology, mid-2000, but it's rapidly developing. So I think now we can see a lot of advances in laser coherence, detection algorithms, computing. At Sintela, everybody always says, 5 years ago, you would go to a conference, you would barely hear about DAS, but now there are entire conferences and workshops dedicated to DAS. So it's rapidly advancing, and there's a lot of research going on around it with governments and civil projects and applications and researchers. One of the exciting things that I think is coming, and we might have it by next year, is that the new interrogators are a lot smaller, lower power, but we're also integrating DAS, DSS, and DTS into that one unit. So before we would have to have 3 huge boxes to measure all 3 parameters, but now with a smaller box, lower cost, we can do multiple parameters on 1 core of fiber. So I think all these advances make it a lot easier and more accessible for industrial applications, for mines and civil projects. To take a small DAS unit and relatively low-cost fiber and look at options of monitoring at larger scale over a long time. So this nano DAS unit I mentioned, again, 6 kilos in weight. We cannot do solar power because of the low power requirements and built and edge processing, so it can be deployed in a field, in a remote location. Which is a lot easier than what we had to do design systems 5 years ago with these bulky systems and a lot of challenges around power and data management. So a lot of those challenges are being overcome quite rapidly with advances in technology. To get the sensitivity of the nano DAS unit over distance and frequency. And then in terms of software applications as well, early on, the focus was on the DAS box itself, higher performance, lower noise. But now that we've got that figured, I think there is a lot of development on the firmware and on the application software, where on your mobile phone, you have the ability to log into your DAS unit, change the parameters, see the events coming in. The events are processed in real time. So there is a lot of advances just over the past 3 years or 2 years. So yeah, I think just ending with, the future of DAS, so looking at induced seismic monitoring applications for DAS. There's applications in civil for tunnels, underground structure monitoring, dams and embankments, bridges and foundations, earthquake monitoring and early warning. There's quite some work, a lot of work going on in that early warning of earthquakes using the existing fiber optics networks in the oceans and in the cities. For smart cities and urban infrastructure, subways, transit systems, there's a lot of monitoring power lines with DAS happening, gas lines, construction zones, another application. And then within mining, there is a whole range of geotechnical monitoring applications with DAS, with underground slope stability and tailing storage facility. Mining is kind of a late adopter, so it's still not as advanced as some of these other applications within government and civil projects. But I think as the technology's cost is diminishing, and developments are happening, and we do more and more case studies and learnings, I think that's a technology that can become more default for a lot of mining applications as well. So yeah, in summary, the key capabilities of the DAS technology is that high resolution of seismic monitoring, and we can even use the existing fiber optics networks for a lot of those civil applications. the detection of microseismic events for subsurface or for civil projects. The system is continuous real-time, and there is a lot happening also on the real-time processing of seismic events with DAS. There has been some good work done with ETH and a few other groups in that area. And then really scalable coverage, it's fairly easy to deploy fiber optic cables over long distances and get measurements in real time. Yes, I think compatibility with existing telecom grade, a few years ago, engineered fiber was becoming known better for induced seismicity, for better signal to noise ratio. But now with advances in DAS, we can get that better sensitivity even with standard fiber. And this is just the last couple of years that we've made advancements there as well. Integration with advanced software for event classification and visualization is rapidly growing. And basically, so I think that's just the summary. It's still a rapidly growing technology. It's still not a plug in and play solution in my view. But I think it is coming to a point where we can use that more routinely for seismic monitoring applications. And I think that's it. Thank you for your time and attention.
Thank you very much, Zara.